Welcome to the rigid body equations of motion. Today we are going to discuss the eigenvalues of the inertia tensor and the principal axis transformation. Previously we have found equation 5.7, and from it you can deduce immediately that the off-diagonal elements of the inertia tensor are equal. So in other words, the tensor itself is symmetric about the diagonal. So in that case, there are a total of 6 independent elements of the inertia tensor. There are the free diagonal elements plus free off-diagonal elements, which will be mirrored upon reflection. And using the symmetrical nature of the inertia tensor, we would want to find a coordinate system where the off-diagonal elements vanish. In such a coordinate system, for example, we would be in a situation where the components of the angular momentum would simply be a product between the corresponding components of the inertia tensor and the component of the angular velocity. So there's no summation implicit here. This is written for each of the three components of the angular momentum, while for the kinetic energy, the contraction of the inertia tensor with the angular velocity vector would reduce to this simple expression, which is of course implicitly summed over the three components, the three non-vanishing components. Now, a vector can be understood either as an object having three components, so for example, you can write it in this way, or as having a magnitude and direction, as given here. And the two angles involved in this expression can be changed to the Euler angles specifying the direction of the new z-axis. If we consider now the moment of inertia of a rigid body for an axis passing through the center of mass, then it is clear that there should exist a transformation which brings it to diagonal form, where R is the rotation matrix expressed in the Euler angles, either through equations 446 or 447, which we discussed in the previous chapter. If the angles are properly chosen in that rotation matrix, then through the similarity transformation here, we obtain the diagonal form of the inertia tensor. These three diagonal components are the components of the principal moment of inertia tensor. The primed directions defined by the rotation matrix in equation 528 are the principal axes or the eigenvectors of the inertia tensor. When knowing the principal moments and their directions relative to the surface of a rigid body, the inertia tensor relative to any other set of axes through the center of mass can be found by a similarity transformation in terms of the Euler angles relating the two coordinate systems. So simply through the transformation here. Then equation 521, which we discussed in the previous section, which was the parallel axis theorem, if you will, can transfer the center of rotation to any desired location. The principal values of I follow from matrix algebra, so the principal values of the inertia tensor. The values in 529 are the roots of the circular equation written here, and solving equation 528, so just to see this, so the equation here, solving this for each root gives the direction of the corresponding principal axis. However, in simple problems, the principal axes can be found by inspection. For example, consider a rigid body as a solid of revolution with the center of mass on the symmetry axis. All directions perpendicular to the symmetry axis are equivalent, leading to a double root in the circular equation. Thus, the symmetry axis and any other two axes orthogonal to each other in the plane normal to the symmetry axis are good principal axes. The principal moments of inertia cannot be negative, as they are given by sums of squares. For example, they are written here for the first diagonal component, and again the summation is implicit in both terms here, summation over the particles of the system. So as such, given that these are positive quantities, the moment can vanish only if all the particles have two of their coordinates equal to 0. That is, they are collinear with the principal axis corresponding to the vanishing moment. Any two axes perpendicular to the line of the body will then be principal axes. This is a limiting case for a body having a symmetry axis passing through the origin. As an example, consider now three equal mass points having the coordinates listed here. So the xyz coordinates of particle 1, of particle 2, and of particle 3. We want to calculate the principal moments of inertia and find a set of principal axes about the origin of the coordinate system. So specifically about the origin. Well, the general definition for the elements of the inertia tensor written for a discrete system of particles is the one here. So if we just apply it, we immediately find this expression for the inertia tensor in terms of the constant b given by the value here. And then we write down the circular equation, and upon solving calculating the determinant, we obtain the result here. So this immediately provides the roots of the circular equation, which are the three non-vanishing values of the inertia tensor in its diagonal form. Now, if you look at the coordinates of particles 2 and 3, you will notice that in the yz plane, the radius of the center of mass corresponding to these two particular particles is rotated by an angle of 45 degrees with respect to the y-axis. As such, we can guess that one principal axis is given by the transformation here. So this would be the I prime axis, let's say. Then the J prime axis is simply going to be orthogonal to it, but still in the yz plane. And then the K prime axis is just their cross product. And it will be given by the original direction of I, so the original x-axis. Then it follows that from these values, it follows that the rotation matrix has this structure, and if we compare it to the general form given in terms of the Euler angles, it follows immediately that the values of the three angles are the ones given here. As another example, we can try to find the principal moments of inertia and the principal axes about the center of mass of a flat rigid body in the shape of a right triangle having the two equal angles of 45 degrees and also having a uniform mass density. Consider the equal sides of the triangles to be of length a, and let the constant b be given by the value here. So the surface of such triangle is given by a squared divided by 2, and then since the mass is distributed uniformly, you can calculate the constant density as the mass divided by the surface, so it's the value here. And then so consider that one of the vertex of the triangle is at the origin of the coordinate system, and that the two equal sides of the triangle are orientated along the x and y axes. And then you can calculate the components of the coordinates of the center of mass of the triangle just through the standard definition, and following with the basic integrals here. So you're just integrating over the mass and the coordinates, and you will obtain these two values. So the radius of the center of mass is given by the value here. Now, what we want to do is we want to translate the coordinate system to the position of the center of mass. And we also want the new x-axis to be along the symmetry axis of the triangle. So it would be along the height of the triangle as drawn from the original position of the coordinate system, so from the vertex to the perpendicular drawn from the vertex to the hypotenuse. And then along this new direction, the x prime value for the x coordinates of the points on the triangle will be in this range. And then what follows immediately is that the y coordinates of the points located on the triangle in this new coordinate system will vary between these two values. So then if we want to calculate the components of the inertia tensor in this coordinate system, we now apply the definition value for a continuous distribution of mass. So it's going to be this is the constant density times a surface integral over the area of the triangle. And generally, so by using the values that we have established here, basically all integrals will be of this sort. So there will be surface integrals between these two endpoints for the x prime and y prime directions from integrated over quantities of this sort. And if you just set out and calculate them explicitly across all components, you will find that the form of the inertia tensor is already diagonal and should be the one given here. So in that case, we can go ahead and establish that one of the principal axes is simply this rotated direction. So we rotated the original x-axis along the height of the triangle, and then we have we can guess that another axis is the one perpendicular to it, and of course we obtain the third one just by their cross product, and this should be parallel with the original z-axis since the triangle is located in the xy plane. And so from these values you can write the rotation matrix down and find that the Euler angles are given simply by the values here. So it's just a simple rotation about the z-axis with an angle equal to pi over 4. Now, if we go back to the original definition of the moment of inertia scalar for a rotation about some axis n, and we write this axis in terms of its direction cosines relative to the laboratory frame, then we can, by plugging this into the contraction that results in the moment of inertia scalar, we can expand the result into the expression here. And then we can introduce a new vector labeled by rho, which is defined as the ratio of this vector n, which defines the axis of rotation, to the square root of the moment of inertia scalar. And by putting these two together, we obtain the equation here, which is the equation of a surface in rho space. So in the space defined by these vectors, the surface which is known as the inertia ellipsoid. So you see, this is a fairly complicated expression, but we can always transform the coordinates such that the equation reduces to its canonical form. So where the principal axes of the ellipsoid are aligned with the new coordinate axes. And this result is just the previous one, but rewritten in a frame where the inertia tensor is diagonal. This is the principal axis transformation previously discussed, and which, again, as stated previously, brings the inertia ellipsoid to its canonical form. The principal moments of inertia determine the lengths of the axis of the inertia ellipsoid. Two equal routes lead to an ellipsoid of revolution, while three equal routes lead to a sphere. To help with the concept, we can try to illustrate it by a simple example. Namely, we would like to answer the following question. What is the height to diameter ratio of a right cylinder such that the inertia ellipsoid at the center of the cylinder is a sphere? We are to consider a right cylinder centered on the origin, having its symmetry axis parallel with the vertical axis, and having a radius given by capital R, a height h, and uniformly distributed mass m. Then, so we can calculate the two equal values of the inertia tensor, so the ones corresponding to the x and y directions, through just application of the standard definition. And notice, so when we are performing this volume integral over the cylinder, the radial coordinate will go from 0 to its maximum value, which defines the surface. The rotation angle goes through 2 pi, but take note that we are integrating from minus h over 2 to h over 2 along the cylinder's height. So we are explicitly calculating this relative to the center of mass of the cylinder, which, given its description, the problem is located halfway up its height. So these two values will be given by the expression here. And for the third value, we perform a very similar integral, which gives the result here. And now for the inertia ellipsoid to be a sphere, these two values have to be equal. So I1 has to be equal with I3, which leads to the condition here. But notice, knowing that the radius of the cylinder is just its diameter divided by 2, what follows is that the height to diameter ratio, which is required in order for the inertia ellipsoid of this cylinder to be a sphere at its center of mass, has to be equal with the square root of 3 divided by 2. Another useful concept is the radius of gyration, which is given by the expression here. So the moment of inertia is equal with the total mass of the system, of the rigid body, as if concentrated in a point located at a radius with respect to the rotation axis, which is known as the radius of gyration. And in terms of this value, the vector rho can be recast as the ratio of n to r0 times the square root of the mass. So the radius vector to a point on the inertia ellipsoid is inversely proportional to the radius of gyration about the direction of the vector. Furthermore, the inertia tensor and all quantities related to it are relative to some particular point fixed in the rigid body. So it's very important to stress this. Changing the point usually changes them, as for example, equation 5.21 shows the change following from shifting the point from the center of mass. Diagonalizing a tensor I prime, let's say, at an axis passing through the center of mass through a principal axis transformation will not necessarily diagonalize the tensor I about some other axis. Thus, the parallel axis theorem has rather specialized and restricted form. In summary, we have studied the eigenvalues and eigenvectors problem of the inertia tensor, leading to the transformation to the principal axis system and the simplified expressions for the angular momentum and kinetic energy in terms of the principal moments of inertia. We have calculated the principal moments of inertia for simple systems like a collection of mass points, a uniform triangular plate, or a uniform cylinder. We have defined the inertia ellipsoid and the radius of gyration, and in the following we will derive the Euler equations of motion. That being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.